Here is part 2 of our 3 videos on the integers. In this video we will concentrate on the integers, and we're going to be talking about division in the integers and the divides relation, along with a quick review of doing mathematical proofs. So just a reminder, the set of integers, as you know, is the set of whole numbers together with their negatives, which can be described in this way. And now the definition of the divides relationship. So we assume a and b are integers. Then a divides b means that there's some integer k such that b is a times k. In other words, there's an integer k for which you can factor b into a times k. The shorthand notation for a divides b is this a vertical slash b. Some alternate terminology, we sometimes say a is a divisor of b, or b is a multiple of a. All three of those phrases have the same meaning. There is an alternate definition of a divides b, and it is a divides b if and only if b divided by a is an integer. This might come closer to how you would think of defining the divides relation, a divides b. But we use the official definition. We will be using the official definition, definition 1. One reason for that is equations without fractions are usually easier to work with. There is one case where the official definition differs from the alternate definition. That's the case where a and b are both 0. So according to the official definition, 0 divides 0. Because you can factor 0 into 0 times 0. You can factor 0 into two integers, one of which is 0. According to the alternate definition, 0 does not divide 0, because 0 over 0 is not an integer, it's undefined. So a few quick examples. 4 divides 52. Because 52 is 4 times 13. You can factor 52 into the product of two integers, one of which is 4. So 4 divides 52. Minus 4 divides 52, because 52 can be factored into the product of two integers, one of which is minus 4. 4 divides minus 52 for the same reason. Minus 52 can be written as 4 times an integer, namely minus 13. And it's also the case that minus 4 divides minus 52. I just did not include it in this list. 23 divides 23, because 23 can be written as 23 times an integer, namely 1. 5 does not divide 21, because there is no integer k for which 21 is 5 times k. In other words, 21 cannot be factored into two integers, one of which is 5. Does 0 divide 17? Well, we would have to fill in this box. We would have to be able to factor 17 into the product of two integers, one of which was 0. Can we find the other integer? The answer is no. No matter what integer we place in this empty box, multiplying it by 0 will not give you 17, it will give you 0. Does 17 divide 0? Here we would have to fill in the box in the equation 0 equals 17 times empty box. Is there an integer that can be put in this box to make the equation true? Yes, 0. So 0 divides 17. 0 does not divide 17. but 17 divides 0. And now here's a list of fairly easy properties of the divides relationship. For every integer b, 1 divides b, because you can factor b into 1 times another integer, namely b. For every integer c, c divides c, because c can be factored into c times another integer, namely 1. For every integer a divides 0. So this is a general statement of the fact we looked at on the previous slide that 17 divides 0. Right, you can factor 0 into a times another integer, the other integer being 0. 0 divides 0, as we noted before, but 0 divides a is false for every other integer a. And then we saw some examples of this fifth point in this list of properties. If a divides b, then minus a will divide b, a will divide minus b, and minus a will divide minus b. When you're checking the divides relation, the signs of the integers don't really matter. Sorry about that little glitch there. Okay, now here is a property of the divides relation that I think is obvious, fairly obvious, but not so easy to prove. So this says if you take a positive integer, b greater than 0, and you have another integer a which divides b, then a has to be less than or equal to b. So for example, if b were the integer 6, the divisors of b, the positive divisors are 1, 2, 3, and 6, and all of those are less than or equal to 6. And if you happen to find a negative divisor of b, it will be less than 6 also. So here's the argument in general. Assume that b is an integer greater than 0 and that a divides b. So according to the definition of the divides relation, this means that b is k times a for some integer k. We're going to do this proof in two cases. The first case is the case where a is less than or equal to 0. If a happens to be less than or equal to 0, then a will be less than or equal to b, because b is greater than 0. This is the easy case. On the other hand, if a is greater than 0, then we solve the equation b equals ka for k, and that gives us k equals b over a, which tells us that k is greater than 0, because in this second case b and a are both greater than 0, and k is the quotient of those two positive integers. So in the second case, k is greater than 0. Since k is an integer, being greater than 0 means it has to be greater than or equal to 1. And then multiplying both sides of this equation by a gives us k times a is greater than or equal to a. And k times a is b. So b is greater than or equal to a, which is what we were aiming to argue for. Here's an example, another example proof, where we're going to look a little bit more closely at proof techniques. This will be a review of Math 211. So we're going to prove this proposition about the divides relation. For all integers n, a and b, if n divides a and n divides b, then n divides a times b. Should be a fairly easy proof. Okay, before we begin, I want to say a few things about doing proofs in general. There are three questions that you should ask yourself at the beginning of doing a proof. The first question is, what are the assumptions that should be made to begin the proof? The second question is, using these assumptions, what do I have to prove? And the third question is it possible to translate the assumptions and the thing you have to prove into equations or inequalities? So let's look at our proposition for all integers n, a, and b. If n divides a and n divides b, then n divides a times b. N asked the first question, what are the assumptions that we should make to begin the proof? The answer is, we will assume that n, a, and b are integers, and we will assume that n divides a and n divides b. There are two general principles at work here, two basic principles. The first is, when you are proving a for all statement, say for all objects x and y of a certain kind, something is true, you begin the proof almost always by assuming that x and y are objects of that kind, and then you have to prove that the something is true. So in the case of this proposition, we are proving that for all integers n, a, and b, something is true. We begin the proof by assuming n, a, and b are integers. And we have to prove the something, which in this case is the if-then statement. The second basic principle is that when proving an if-then statement, say if a then b, you assume a is true, and based on that assumption, you have to prove b. So we are proving if n divides a and n divides b, then n divides a times b. According to the second basic principle, we would assume the hypotheses of the if-then. In other words, we would assume that n divides a and n divides b. Second question for our proposition. Using the assumptions, what do I have to prove? Well, the basic principles that we just looked at tell us that. Using the assumptions, we have to prove that n divides a times b. Right? When proving an if-then statement, one of the assumptions is the hypothesis of the if-then, and we have to prove the conclusion. So answering the second question also uses those two basic principles from the previous slide. And now the third question, is it possible to translate the assumptions and the thing we have to prove into equations or inequalities? And the answer is yes. The definition of divides will give us a way of translating into equations. So n divides a and n divides b is equivalent to, according to the definition of the divides relation, a is k1 times n, and b is k2 times n, for some integers k1 and k2. And the thing we have to prove, n divides a times b, using the definition of the divides relation, is equivalent to a times b is k3 times n for some integer k3. So this gives us a start on the proof. You write down the assumptions, assume a, b, and n are integers, and that n divides a and n divides b. Then we write down what we have to prove. Then we translate into equations. We translate the assumptions into equations. As a consequence of the definition of divides, a is k1 times n and b is k2 times n for some integers k1 and k2. And then we note what we have to prove. We have to show that n divides a times b. That is, we have to show that ab is k3 times n for some integer k. So asking and answering the three questions does a couple of things. It gives us a start on the proof, as we saw on the previous slide, and it gets us to a point where we can see what really has to be done in order to prove the proposition. In this case, from the assumptions, from the statement that a, b, and n are integers, and a is k1 times n and b is k2 times n for some integers k1 and k2, we have to derive the statement that a times b is k3 times n for some integer k3. So roughly speaking, from these two equations, a is k1 times n and b is k2 times n, we have to derive this equation, a times b is k3 times n. That's a slight oversimplification. So here is the entire proof. The first part we've seen, assume a, b, and n are integers, and that n divides a and n divides b. Then a is k1 times n and b is k2 times n for some integers k1 and k2. We have to show that n divides a times b. In other words, we have to show that a times b is k3 times n for some integer k3. And now the argument for this equation. Well, in order to prove this equation, I'm going to start with the left-hand side, do some legal operations, and end up with the right-hand side. This is sort of a typical way of proving that an equation is true. So by our assumptions, a times b is k1 times n times k2 times n. Right, I've replaced a by k1 times n. I've replaced b by k2 times n. With a little rearranging of the order of multiplication, that can be written as k1 times k2 times n, and that is k3 times n, where k3 is the integer k1 times k2 times n. That finishes the proof. We note that k1 times k2 times n is an integer by the closure properties for the integers, and this square is the standard symbol for the phrase, "this completes the proof." Okay, one more example sort of along the same lines. Now we're going to prove that for all a, b, and c, if a divides b and b divides c, then a divides c. What are the assumptions we should make to begin the proof? Well, we're proving for all integers a, b, and c. If something happens, we should assume a, b, and c are integers. The something is an if-then, so we should assume the hypotheses of the if-then. We should assume a, b, and c are integers, the standard start to a proof of a for all, and we should assume that a divides b and b divides c, because we are proving an if-then, and that's the hypothesis. Using the assumptions, what do we have to prove? We have to prove the conclusion of the if-then. We have to prove A divides C. Is it possible to translate the assumptions and the thing we have to prove into equations or inequalities? Yes, as before, we can use the definition of divides. A divides B, and B divides C is equivalent to B is K1 times A, and C is K2 times B, for some integers K1 and K2. And the thing we have to prove, A divides C, is equivalent to C is equal to K3 times A, for some integer K3. And now here's the complete proof. We assume that we write down the assumptions, we translate into equations, assume A, B, and C are integers, and that A divides B and B divides C. Then B is K1 times A, and C is K2 times B, where K1 and K2 are integers. We have to show that A divides C. In other words, that C is K3 times A for some integer K3. And we will prove this equation as we did before by starting with the left-hand side. By our assumptions, C is K2 times B. And now we replace B by K1 times A. So C is K2 times K1 times A. And this is equal to K3 times A, where K3 is the integer K2 times K1. K2 times K1 is an integer by the closure properties for the integers. And here's the square. This completes the proof. We have proved what we needed to.